Any questions? All right, so let's go through the lecture first. And for everyone who hangs in down to the bitter end, I can then follow up with a few tantalizing hints for the final. So this is the last section on trees in the books, and we're talking about tree traversals. So you have a tree and you want to visit all of the elements of the tree in some order. And so there's all sorts of different orderings, and if this was a more conceptual and less of a programming class, we would test them all in the final, but we won't. So we start with in-order traversal, and in-order traversal is something that you've already seen, you've just not seen the name, where you say, okay, before looking at what's in the root of a tree, you look at the left subtree. Then you look at what's in the root, and then finally you look at the right subtree. So that's in-order traversal, and you can do this for any old tree, but when you do it for a binary search tree, then it lists the nodes in sorted order. The reason is, if you remember, a binary search tree, everything in here is less than the root, everything here is greater than the root. So if you first list everything less than the root, then the root, and then everything greater, then it comes out in sorted order. So that's simple and that's useful. And you've certainly done that in the previous section. Now, when there's in order, there also are two other traversals called pre-order and post-order. And abstractly, they're simple enough to understand. When you have a tree with a left subtree and a right subtree, in order, we first looked at the left, and then at the middle, and then at the right. But with pre-order, we're going to reverse that. We're going to first look at the root. Then we're going to be looking at the middle, at the left, and then at the right. And actually, it makes sense for any number of trees. If this tree was an n-ary tree that, say, had 3 children, then you could look at those children. So pre-order means you first look at the root, and then you look at all of the children, however many there may be. In order only makes sense for binary trees, but pre-order makes sense for arbitrary trees. And post-order is the same thing, except you first look at the children and then you look at the parent. And so that's all abstract stuff, and you wonder, is it useful for anything? And we'll get to that in a minute. So right now, just from the abstraction, just look at this pathetic little tree here and tell me what are the various traversals. All right, so the in-order traversal, we look at this subtree first, and then we look at its in-order traversal. Well, so we start at the root because there's nothing on the left, and then the thing to the right. Now we have the root of this tree, that's f, and this one to the right. So we've eliminated 2. So for pre-order, it certainly starts with f. Then we do the pre-order traversal of this tree here, and then we have r. And so in the pre-order traversal, we have to first do the root and then the thing under it. Then for the post-order, is post-order always the backwards of the pre-order? No, it's not, right? Because you're still visiting the children in the same order. So we're actually going to have to do it. So for the post order, I know I have the f at the last. I guess I must have the r before that, and then I have the post order here. So E D R F. Do we have this as a choice? F D E R. So that's number 1. See what everyone did. What? Am I right? That was the number 1? D, E, F, R. F, oh no, F, E, F, D, E, R, D. So it's something else. Yeah, let's see what you guys said. Okay, most of you said it's 3, so how come I got something different? Someone help me out here. What did I do wrong? So this is post order, that's right. F. Oh, that's right. Okay, you got it right. I have no idea what I did wrong. Okay, I have to watch my video. All right, so that's reasonably easy. So now, whenever you have these definitions, I mean, there's no point to a definition if it doesn't yield something useful. And so whenever you see a definition like that, the first question you ask is, okay, fine, that's a perfectly wonderful definition, but what's it good for? Why would I ever care about a post-order traversal of a tree? And so here is a typical example. When you have an expression tree, you know those expression trees where the leaves are numbers and the nodes in between are operators. When you have an expression tree and you do a post-order traversal on it, then you get something that's potentially a little bit familiar from the stack lecture. So if you look at the tree here, if I do a post-order traversal, I start at the root 3, 4 plus, and then 5 star. So again, I did 3, 4, followed by plus, and that entire thing followed by 5 and the star. And that's the reverse Polish way of writing this expression. Now push the 3, push the 4, add them together. That together was 7. Then you have 7 and 5. Multiply these together for the result of 35. So the post-order traversal of an expression tree gives you reverse Polish. And that is potentially useful because when your Java compiler parses your program, it actually builds up a tree. So it builds up a tree that looks very much like this. The tree is much bigger than that because it has also nodes for the entire program file, for each class, for each method, for each statement in the method. And so it's a big old involved tree. And the ultimate job of the Java compiler is to create Java bytecodes that the virtual machine can compile. It does exactly this when it comes to translating expressions. It prints the expression tree in post order, and out come the instructions for the virtual machine. It's a stack-based virtual machine. So this is actually something that's reasonably useful and good to know. Now here's what I think is an even more compelling use, because this is something that sometimes you have to do. Ideally, you would think that this is something that's in the library of your programming language, but it often isn't. So imagine that you're coding away on something, and this is something that I had to do in CodeCheck, for example, and now I need to clean up. So I've generated a bunch of student files, and now the job has come to clean them up. Of course, I could shell out to the operating system and run RM, but that is expensive to shell out. It would be cheaper to just do the cleanup inside the Java program. So what do I have to do? I have to remove all of the directories that are under some parent directory. You would think that there would be a call in the Java library, like files remove all. But for whatever reason, they've never gotten around to do that. And so you actually have to program that by hand. And you might end up at some point having to do this in some other programming language, like Objective-C on an iPhone. And there it doesn't exist either. So it oftentimes does happen that you need to do this erasing a whole bunch of files and directories by hand. And when you think about it, you're going to get some tree operation. You're going to get an operation that says, list me all of the files and subdirectories of a directory. So you can operate on a tree a node at a time, where a node is a directory. But you still then need to traverse that in post order, because you first need to empty a directory before you can remove it. If you try to remove a non-empty directory, you're going to get an operating system error. So that's a typical case of post order traversal, where I'm going to traverse my directory. I'm going to go here and say, not yet. I'm first going to move to this one and to this subdirectory. Then I'm going to erase all of the files in there. Then I can nix it out. Then I'm done with the children of this one, and I can get rid of this one. And then the same thing for the right subtree. I can't yet remove this one because it still has children. Visit all the children. And so that's post-order traversal. So one way of remembering post-order traversal is that's what you need to do in order to zero out a directory tree, a common operation. Pre-order is the exact opposite. Pre-order you need when you want to copy a directory tree. Also a common operation. You have a bunch of directories and files, and now you need to make an exact replica of that. Now, one would like to think, again, that this is built into the programming language, but it often isn't. And so when you code it by hand, you make a pre-order traversal of the directory tree. You first visit the root and make a copy of it. And then for each of the children, you need to first make a copy before you can copy any files. There has to be something there. So poster child for pre-order, you first visit the root and process it, and then you visit the children and do something with them. Because if you don't make a copy of the root, then the copies of the children have nowhere to go. So here we have another great clicker question, much better than the first one. So now suppose I have two directory trees that already exist, and now I want to find out whether they are the identical tree, same subdirectories, same files in there. That might be, your first starting point for the plagiarism checker, right? You want to know whether two submissions are exactly identical. And so when you traverse the directory tree, which scheme should you use? So I'm giving you these four choices. All right. So here are the votes I've gotten so far. Feel free to add your own. So very few people said that in order was the right way. And there's a good reason why in order isn't going to work, right? In order only works for binary trees, but directory trees are not necessarily binary. A directory can have any number of children. So a large number of people said it's got to be pre-order. So let's see. So I have some directory trees, and then I'll have another one in here. And so what would pre-order here mean? That means I would first look at all of the files in the root directory. And if the files in the root directory are all identical, or at least have identical names or whatever I want to check, I want to look at the subdirectories. Okay, so I would look at all of the subdirectories in here. And if they all have the same subdirectories, then I keep on going. And that makes perfect sense. That'll surely work. So now the only question is, would post order also work? And I guess that's a little iffy, right? Because what does it mean for post order to work? Like in a situation where we're here. So let's look at these two here, and now we're making the decision, should we look at the root? We don't really know what to compare until we've looked at the root. So I guess post order wouldn't work so well. Because we would, the only sensible way of doing this is you ask this node here, what are your children? And then you compare them one by one. But you've got to ask it, what are the children? You've got to visit it first before you can really progress. So I think that pre-order is in fact the right answer here. But it's not so totally obvious, partially because didn't exactly tell you what those operations were. All right, so that should give you a bit of a food for thought as to how this traversal works. But now comes the thing that oftentimes people learn this traversal in an abstract algorithms book, but it doesn't help you if you actually want to put it to work. So if you want to put traversal to work, you need something else. You need some way of actually applying it to a real-life tree. And I've seen more than one tree library that didn't give you this way of doing it. So if you actually want to have a useful tree library, it better give you some way of actually carrying out the traversal. So here's how you would implement it. So I'm just doing it for pre-order because the other ones are identical. So this is a standard trick, which, by the way, you will want to know for Friday. So whenever you have a method that does something recursive on a tree, remember trees are not recursive, at least the standard trees that we have. The nodes are recursive. So you always need to have a non-recursive function on the tree. And then you have to have some way of making it recursive. There's two ways of doing it. You could make a recursive function that takes a node as a parameter, or you could make it as a method on the node. Either way, it's the same thing. So you always need to have the non-recursive function on the tree, and then some way of making it recursive. On the thing that you're going to have to do on Friday, it doesn't really matter which of the two ways you make it. When I say which of the two ways, whether you make it as a static function or if you make it as a method of the node class, either way will work. And you just need to make that decision. The reason that the static methods are sometimes easier is this here, that then you don't have the extra null case. So here we're saying if the node is null, then we do nothing. And for the children, we visit the children by calling pre-order. But that begs the question, what the heck are we doing with the visited node? And we want to do something with it, but that something could be any number of things. Maybe we want to inspect what it contains. Maybe we want to copy files or delete files or print it or do some counting or who knows what. And so because it's different every time, you do what you do when something is different every time. You design an interface. That's what one does in Java. And says, we don't really know what we want to do. Remember the good old measurable interface? We knew we wanted to get some number out of it, but we didn't know how that was going to go, so we had an interface. Here we have equally an interface, the visit interface. And we don't know what it means to visit this object. It means to do whatever the particular visitor wants to do. So at this point, we just call visit on the visitor that we get. So you have an example on how you can put this to use. Suppose I have a tree of names, and I want to count all the short names in the tree. And here's the way you do it. You make some class that implements the visitor interface. And so what do we want to do? In the visit method, if the data is short, if it has length at most 5, then I'll increment a counter. What counter? Oh, the short name counter has a counter instance variable. Notice it's a public instance variable. I'll come to that in a minute. So now I make myself a new short name counter. This is an object that is a visitor that is willing to be called repeatedly at every node. I'm telling my binary search tree, do an in-order traversal. I don't know why it says in-order here. I mean, here we had in pre-order. Could equally well say pre-order. When you do this kind of counting, it doesn't make any difference in which traversal you use, because you're just inspecting each node. So, but for whatever reason, here it says in order. So we're saying, you binary tree, call the visitor at every node. And in the end, this object V has the counter incremented. It's only one object that gets passed from node to node to node, and the counter gets incremented every time that we had a short name, every time something exciting happened. And then in the end, I just say, what is the value of the counter now? So here, because this is a local class, I didn't really have to worry about making this instance variable private, because that local class can't be used by anyone else. It's gone after the method exits. So I felt no shame in making this a public instance variable. So that's how you would use a visitor, and it's a common pattern. You just make an instance of the visitor interface and you run it on the tree. Yeah, it occurs to me that you could use that to solve one of the exam problems, but that would be okay with me. Now the thing with the visitors is you will not actually see visitors when you look at the standard Java library. It's a reasonable thing to do. They could have offered us a bunch of visitors for breadth first and depth first and whatever, but they didn't. Some tree libraries do that. The Java library always is based on this concept of iterators. And so an iterator is kind of like a visitor, but it kind of walks slower. It walks a step at a time. So when you do visitation, you always visit the entire tree. And that's fine when that's what you want to do. But now suppose you wanted to do something that doesn't necessarily affect the tree. Let's say you have a large tree and you only want to see the first 10 nodes. Now why might you want to do that? You have a user interface and you want to show the user the first 10. And then the user clicks next and you want to show the next 10. But you don't want to produce all 2 million at once, because the user might lose patience and you might never need them. So for that kind of thing, an iterator would be better. And so that's why the Java library gives you an iterator. But the way an iterator really is done is, as you know from your homework assignment, an iterator can be made out of a visitor by using a stack. So you push the visited nodes on a stack, and you just have to have some way of suspending the visitation. And do I want to go into this? No, because you've done this in the homework assignment. So I just want to contrast that iteration is what you normally find in real-life libraries, because it does have this extra useful aspect. So with iteration, you can do everything that you could do with the visitation pattern. Now, it would be nice if they gave you multiple kinds of iterators. They give you, in essence, an iterator that matches in-order traversal. They could give you an iterator that matches pre-order and one that matches post-order traversal. They just haven't done it. That would be another great homework assignment next time I teach this class. All right. A couple more concepts that you will find useful in the next class. Depth-first search. So when you think of pre-order and post-order traversal, they're useful in some contexts, like I said with the directories. But sometimes you want to traverse a tree in a different way. You want to say that you're interested in the deepest nodes first, or let me actually switch to breadth first, because breadth first is so much more intuitive. With breadth first search, you say, I want to first look at the root, and then I want to look at all the children, and then I want to look at all of the grandchildren, and so on. I mean, that obviously sounds like a useful thing to be able to want to do. And so the way you implement that is that you visit the root, and then for each of the children, you put the children in a queue. And to make it look nice, you put them in there in reverse order. So here I've put in the children in this queue. Now I dequeue the front, that's B, and now I put its children, those are these ones here, at the end of the queue. Then I dequeue the D. Oops, sorry. Oh, it's a picture. And then I put its children at the end of the queue. Then I dequeue the E, and I put its children, that's these ones here. Oh, here, there, at the end of the queue. And at this point, you can see I have them all flattened. I have all of the grandchildren here flattened up. So the queue does a good job in doing this. You just have to remember when you push them into the queue, you have to push them in reverse order. That's what's called breadth-first search. And I think breadth-first search is pretty intuitive. You go like this, and like this, and so on. Yeah?
What are some applications where you would have to use breadth-first versus depth?
You're going to see that extensively in 146. So when you search through a graph and you want to look at the immediate neighbors first and then at the neighbors of that, then you would use a breadth-first search. You'll see at least 5 different applications where you want one or the other, and you'll know. So right now I'm just dropping these names and telling you you'll need it later. And they'll teach it to you again. So depth-first search is the opposite, where you use a stack instead of a queue, and it's less intuitive, and it's not easy for me to come up with a super useful example right this minute. But basically, you try to go in as deeply as you can, and so so here we're pushing the children again, and so that way you get into the leaves of the tree before you look at much of the rest of the stuff. And so I really don't want to say anything else about it because it's not going to happen for anything in this semester or in the final. Okay, I guess I do need to say enough that you can answer the clicker question. So let me do this in slow motion after all. So, and I'll just have to do it again. For some reason, I always find this unintuitive. So I'm pushing the children, and again, I'm doing it going right to left off the stack. I am now popping off where am I popping off? B. I'm now popping off here, that's this one here, and oh yes, that's how I go down. So I'm popping off here, and so I'm forced to go a level further down, so, and I do it again in reverse. And so that's the way I get as quickly down to one of the leaves in this fashion. So now that you know that, now answer this question here. Can it ever happen that the breadth first and the depth first traversal of a tree are the same? So this is a typical interview question. So we have a tree with n elements So what does it mean if it has n elements and the height is also n? What does it look like? It's like a line like this, right? So that would be A, B, C, like this. Notice these are n-ary trees, these are not binary trees. So that's a valid tree. So try it out. Make the depth first traversal and make the breadth first traversal and see if they're the same. Now, if you have a tree whose height is 2, that would mean it has a root, and then it has some number of children. So try it out. Make the breadth first traversal and the depth first traversal and see if they're the same. So I think this other distractor here, if it's not a binary search tree, that sounds kind of bogus. I mean, why would it have anything to do with anything? So I'm tentatively going to say that I don't believe that. So now one has to reconstruct that algorithm. So the breadth first search algorithm says you have, what do you have, a queue or a stack? A queue, right? And so you have the queue, you push the nodes in the queue. So we're pushing A. We're pushing B. And now what are we doing? So we're pushing A, and then we're removing A and pushing B. We're removing B and pushing C. We're removing C and pushing D. So we're visiting them in this order. What do we do in depth first search? Okay, so I'll leave you with that. So how about for this one here in breadth first search? We're pushing A. Then we're removing A. And we're pushing these ones in reverse order. So that way they come out in the queue in the right order. G, H, B, C, D, E, F, G, H. So we'll again visit them as A, B, C, D, E, F, G, H. What is depth first search? So use a stack instead of a queue and see if you get the same. So let's see what people are doing. This is okay. So a lot of people seem to think that this one here is the right answer. I'll just make it with 3 elements. A, B, C, So breadth first search means we just went through this. It was A, B, C. And now the depth first search. So we're putting A on a stack. We're popping it off and replacing it by its child. And we're popping that off and replacing it by its child. Yes, it does seem exactly the same thing as well. So this is correct. Well, let's make sure that this one is wrong. That would be the case where we had A, B, C. In this case here, for breadth first search, we're pushing A on a Q. We're removing it and then pushing B and C. For depth first search, now we're pushing A, then we're pushing. Huh? Thanks. Oops, I now lost the whole thing. So anyway, it also works. It also works. So the right answer seems to be that you were both right. All right, so why did I cover this? Because I got paid to do it. So I don't actually care about this for 46B very much. It was really a warm-up thing for 146. And so I don't even want to go into this anymore. So instead, let me spend a few minutes just going back to what we've learned instead of this iterator stuff. And so that you get a retrospective of what I felt what the course was all about. So I really liked the idea that the very last thing you saw was interfaces again. Interfaces are important and useful, and you're going to be seeing them much more. So you've seen plenty of interfaces by now. You've seen, of course, those toy interfaces, measurable. You've seen comparable, comparator, which you will need all the time in practice. You've seen that things like list and map are actually interfaces, and that's somewhat useful when you have a map. It could be a tree map or a hash map, and so you can write algorithms that work equally well for both. And you've seen now this visitor interface. So interfaces are really useful, and interfaces are also really easy. There's nothing to an interface. There's a bunch of methods that are abstract. You need to implement it. Or if you want to use an interface, there's a bunch of methods, and you can call them even if you have no idea how they're implemented. Those are the two things. In the final, this will happen. You will be given an interface that you've never seen before, and you will be asked to make use of it. You will be asked to say, given a class that implements this interface, put its methods to work, even though you don't know what those methods actually do. So that's, and it'll be in a very familiar context. If you review some of the past homework assignments, I don't think I'll give anything away if I say it has something to do with recursion. Review some of the recursion homework assignments, and it should make perfect sense when you see it. And it's only a few lines of code. You just need to figure out how to do this in the somewhat abstract context. The other thing I will ask you is, hey, here is a class that should implement this interface. And of course, then you need to implement its methods. It'll be a familiar class that you will have seen several times. Yes?
Will those be similar? Like, first do the abstract, kind of, dealing with the methods, and then you do the same?
It'll be eerily familiar, yes.
Meaning?
I mean, when you will understand from the context. If you have done your homework and if you have reviewed your exams, you can't go wrong in that one.
Are they kind of two more questions of the same classes and interfaces? Meaning, like, first, if you use the abstract method and then you implement actual methods.
Yeah, that's exactly right. But the way I've done the test cases is, just in case someone knows how to do one without the other, that the test cases are separate from each other. You could then go ahead and write a combined test, but you won't have time for it. So yeah, don't do that. You can do it after the exam. That's actually a nice exercise. So also, if you remember at the beginning of class, we had a whole bunch of input-output. And you may wonder, why did we have all of this input-output? And it seems completely unrelated to the rest of the class. And so historically, this has been ping-ponged back and forth between 46A and 46B. And so there were times when interfaces and inheritance were not taught at all in 46A, and they were only picked up in 46B. And then people felt, gosh, this is something that students really need to see twice. Because the first time you see it, no one understands anything, and the second time, it becomes a lot clearer. And so then input-output got shunted into 46B. And the other excuse was, well, you need exception handling to do input and output, and you really can't understand exception handling if you can't understand inheritance, because exceptions form an inheritance hierarchy. The reason I actually like it here in 46B is it was the first thing where you had to do algorithmic thinking. That to do this, in particularly parsing input, is non-trivial, right? You have to come up with your own algorithms. This is not something where there's any standard recipe. Every input file looks different, and you have to come up with a scheme. Say, okay, fine, I'm going to skip past all of these things until I find something that has only digits. Or I'm going to look at everything until I find something that ends in a period, or whatever. So that algorithmic thinking, I think that's what makes the input-output interesting and teachable, that it's just something different every time. Then, of course, there's recursion. Recursion is big. Everyone needs to know recursion. And what I liked in this course is that almost all the recursion that we did was interesting recursion. We did very little of the factorial or sum or kind of linear traversal recursions. Almost everything we did is we broke something up into lots of other problems, and each of them got broken up into lots of others. Yes?
Will there be a polygon?
I won't confirm or deny whether there will be a polygon. But, if you remember that polygon, the reason I love the polygon is, even though you don't, it is the poster child for the visual poster child for recursion. Here I'm cutting it up into two smaller things. What's not to love? The reason you don't love the polygon is because you're resistant to the idea of applying the algorithm that's been presented to each time with the corners, right? So you have the corners C0, C1, C2, C3, C4, C5. And the thing that made the polygon difficult was that you had to oh, actually, we never cut it like this, right? We always cut it at C0. Let me do this nicer, because otherwise I'm not getting my point across. So we had it at C0 and at CK, right? And then this one was Cn minus 1. And what baffled everyone with the polygon, and a good number of people the second time around with the polygon, and I hope it'll never baffle you again in your life, is that the corners are funny. This thing here is a 6gon, right? The big thing is a 6gon or a hexagon. What do I break it up into? I am not breaking it up into 2 3-gons. Yeah, this lost its screw or something. All right. So I'm not breaking it up into 2 3-gons. I'm breaking it up into 2 4-gons, right? And so you have to, when you made those, the confusion was you had to go to CK, and that's fine. You just had to make sure that K was large enough. But then on the other one, CK was in both of them. If I had $1 for every time where I had to say, that CK wasn't in the second one, that would be good. And also C0 is in both of them. So if, God forbid, there was another polygon on the final, remember this point, that where you cut it, the 2 points where you cut it, C0 and CK, are in both of the polygons. So if you have a 6-gon, then there are 2 4-gons and not 2 3-gons that come out of it. All right. So, but we've had all these other interesting cases of recursion. You've had the case where we broke down numbers into bits and pieces, which was an artificial example. We had the one with a number puzzle, which could be applicable to any old puzzle. So that was a good example. So recursion is just this general problem-solving technique that everyone needs to be able to know. There are many problems where to do them without recursion would be really difficult. Remember, to iterate is human, to recurse divine. Sorting and searching. Why do we have sorting and searching? Because one always has sorting and searching in CS2. Of course, you will need to use sorting and searching algorithms, so you need to know what is binary search. You need to know a little bit of how a sorting algorithm might work, but more really why it's there, it's algorithms. It's to show you that there are non-trivial ways of thinking about an algorithm that makes it go much faster. Everyone can sort. I mean, how hard can sorting be, right? You pick the smallest one and then you pick the next smallest one from the rest and so on. That's selection sort. But would you have come up with merge sort? Maybe, maybe not, right? Merge sort is not intuitive. Or it took, in fact, computer scientists about 10 years after the first computers were built to come up with merge sort. So merge sort is not the most obvious thing. And so it took them a while to realize that, that efficient sorting is there. So what do you have to know about sorting for the exam? I am not going to ask you to implement merge sort. I am not going to ask you to implement selection sort. I'm not going to ask you to implement crazy sort. But I will ask you to do something that uses a part of one of those algorithms. So if it were to say, now you can start thinking, which of these algorithms really have parts? Does selection sort have a part? I guess the part is finding the smallest element, or swapping 2 elements. So think about that. So I will assume that you're familiar with a part of an algorithm that is used in one of these sorting algorithms, and then you can put it to a somewhat different use. You will not have to implement it. I will give it to you. But when you see the implementation, you should be able to say, oh, that's what was in the book, and you will then put it to that somewhat different use that's not actually sorting, but similar. So big O is big, of course, and you're going to see much more about big O in 146. You've seen the basics of it, and what I think went well in the course, even though not everyone might agree on how well that went with everyone, is that it's very common to see students in 46B memorize 6 or 7 big O things and then just try to regurgitate them on the test. And that's, of course, not a very useful skill. We can surely find people who memorize things in all over the world and pay them if that's something we want to do. But so the memorizing the big O by itself is not useful. The question is, can you look at a new algorithm and estimate its big O? Can you see, is there a linear traversal? Is there a double loop of a traversal of traversals? Does stuff get cut in half every time so that you can actually have a log n step? Does it involve sorting, which, as you know, is at least n log n? Which of those dominates which? If you have a sorting and then a linear traversal, then the sorting dominates. That's the kind of thing that we've had in the second exam. There won't be much in the final because I don't have time to do the grading for it. There will be a question where it says, given an input of size n, come up with a O of something algorithm that processes it in a certain way. So at that point, you will need to look at the algorithms that spring into your mind and see, is this really good enough? So if you come up with a basic loop that does it, you have to check, does the loop work? Is it going to give you the performance that you need, or do you need to go to a tree or a hash table or some such other data structure that gives you something better? So, and that's how you're going to see big O in the exam. But of course, you're going to see big O many, many times in your life. So data structures. So you've learned all these useful data structures, lists, stacks, queues, sets, maps, and they will be with you forever. I mean, one uses those things all the time, and they're just basic plumbing. You've seen linked lists, all of those wonderful nodes, and so you've done this much more intensively than I've seen most people do, because I think we've done the right thing with all of these diagrams and the debugging and all of that. Those are incredibly useful skills when you have to do that. May not happen very often in your life, but when you have to do it, then that's useful. And the other thing that I hope that everyone has remembered from particularly that lab where you had to debug the linked lists is, what is the single most useful tool when you use the debugger? The piece of paper on which you write down all of that ephemeral information that you gather, right, where you make the little sketch. So if you have a reasonably complicated program, the debugger is only so good. It can trace you through and stuff. But more often than not, you have to have a piece of paper where you write down what you note, what you observe. Because you're using the debugger because you don't yet know what the mistake is. Otherwise, you wouldn't be using the debugger. And so this happens all the time, that you're encountering strange things, complicated relationships during debugging, and you have to keep like a little sheet of scrap paper with you and write down these things, some of which might be useful later. That's what people do. I guess you could take a screenshot or a movie, but I don't think it's as effective to flip through it later. I've seen debuggers that basically take a movie, but somehow no one ended up using them. So, but this idea of being able to deal with linked lists is, in that way, at the node level, is a super useful skill, and I'm glad that we spend a lot of time on it. Trees, trees are a useful data structure. I'm not going to say too much about them because this really was meant as a warm-up for 146. It's again one of those things where when you see them the first time, then it's kind of overwhelming, but when you see them the second time around, then it becomes much better. So, oops, no, my slide got messed up. Let me fake them into the slides that I wanted. Oh, yeah, that's fine. All right, here's the next slide that I wanted. So, what really matters? So there's really only three things that I think are really super important when you look back at this course 20 years from now. The first one is the whole algorithms things. Algorithms are big. Big O is big. Recursion. And the other thing, I think that you will look back on a pseudocode. You'll say, oh, I had this horrible instructor, and he made me write actual pseudocode, and there were these rules for writing pseudocode. And I actually got better at writing pseudocode. I hope many of you will have had that feeling. If you don't have that feeling, go back to Piazza in week 1 or 2 and look at some of the pseudocode that was up there. And I think you will realize that it wasn't a total loss. With data structures, you need to know your data structures. The one data structure that everyone needs to know is the map. If I only had one data structure on a desert island, make it a hash table. There will be one assignment on the final where you have to do something with the map. You're going to have to put things into the map, get them out, count something, some such thing. There was a problem in the last exam, and half of you got assigned the array version of it, and half of you got assigned the map version of it. And so I would strongly suggest that you all look at both versions. It's very instructive to see them both next to each other. And so something like that will be on the final. There were a few students who completely abused the map and who messed up the keys and values. And so if you're among those, by all means, have another look at that. It's very important that you get that right. These things are pretty easy to do, but, and there will be something like that on the final. Yes?
I didn't catch what you just said about the maps. What did you say about that?
So there were some students who, so the thing that you had to do is make a frequency map. So this was something you needed to count some things. And so when you make a frequency map, then the keys are the things that you're counting, like 1, 4, 9. And the values were how often they appear. Like the 1 appeared once, the 4, first it appears once, and then it's twice. The 9, oh, and then it's actually later 3 times, and the 9 appeared once, and so on. So these are the keys of the map and the values. So the values are the counts. And I guess here's why it's confusing. And the keys are the values of the input. So make sure you get that part straight. And so this basic idea that you are associating some properties of the inputs, and in this case the counts, that's something that's going to be tested. And as with all maps, what do you need to remember? Whenever you write anything that involves a map, the first time is special. Now, there's always that awkward thing when you've never done this before, and so there's nothing in the map yet, and so the code always has a special case for that. So keep that in mind. All right, so maps. And so linked structures matter, but I guess what matters more than what linked structures is planning, attention to detail, patience, and debugging. So the reason that I bugged you with these rings and iterators and all of that was not because you'll ever have to do that again, but because it's a complex piece of structure where you have to keep a lot of things in your mind, and you can't just code those by trial and error. Has anyone succeeded getting anywhere with trial and error? I would gather that would be an extremely lucky person, right? So really it's the planning aspect that to me was important with this. But they're important structures, for sure. So next semester, you'll have 2 separate courses. You can take them both in parallel if you like, or you can take one after the other. There's CS 146. So it's a much more theoretical course. So the big difference, I think, in 46B and 146 is, the subject matter is pretty similar. But in 146, they assume that you can code everything. So they will often just give you, without any code at all, they will give you the data structure or an algorithm, and they'll run it through you on the blackboard, and then they say implement it. And then all of the choices of implementation, where do you use an array, where you use nodes, and that kind of stuff, it's assumed that you know how to do that part. So it'll have more sophisticated data structures. It'll have these nifty self-balancing trees. It'll have graphs and so on. And it'll be much more formal about Big O. So we've been doing a lot of hand-waving Big O, and there you'll see it with some actual mathematics behind it. At that point, everyone will have completed Math 42, so there'll be at least some mathematical foundation behind it. But it's a very important course, And someone said in the discussion group, it's harder than 46B. And I would imagine that's true. It is more abstract and it requires more that students can think independently. Then there's CS 151, and it's called Object-Oriented Design. And so that starts off with interfaces and inheritance. We have no faith in you guys. We teach you interface and inheritance in 46A. We do it again in 46B, and we do it again in 151. But by that time, everyone will really have gotten it. And so it's the foundation of what you need to design more complicated programs. So there'll be a whole thing on design patterns that teach you how to do larger programs, and you'll have a group project. Unfortunately, in this curriculum, there are not as many group projects as we would like, so this is one of the 2 required group projects that everyone will go through. So hopefully your instructor will make good use of version control and Git. And so again, I feel sorry that I didn't push that one as much as I had. All right. So now here I have an unhappy slide. So first of all, does anyone know who these people are? Yeah, so the first one is Mr. Reagan, a well-known actor. Here he's starring in a movie called Bedtime for Bonzo. Bonzo is the chimp. The fellow under here is another well-known actor. His name is Mr. Schwarzenegger. And so as you know, after a successful career in acting, both of them had a decidedly less successful career as governors of California, in which they created real damage. So you may not know this, because this happened in 1960. In 1960, the California Master Plan for Higher Education was unveiled, and it was a model for the world. And there's still many parts in the world that follow this model, where there's a 3-tier system for higher education. There's the research universities, University of California, Berkeley, UCLA, and so on. There's the California State Universities, the most important part of the system, that are there for people who want to become successful in a profession, but where that profession is not likely to be research. And then there are the community colleges for people who need some college experience, but who don't need a 4-year degree. And it's, as you know, possible to go from the community colleges to the CSU, and somewhat possible, certainly it's possible to get an undergraduate degree in the CSU and then get a graduate degree in UC. So the system was designed so that at every level that you had a well-defined audience. And so for the CSU, as you know, the top third of high school graduates is allowed to enter the CSU system, and that goes for every high school. So you don't have to compete with the best high school in the country and in the state, but in every high school, the top third is guaranteed admission into the CSU. It used to be you were guaranteed admission into your local. That's how the system was designed. It was designed to say that you would guarantee admission into your local or any campus of your choosing. You would be able to choose your campus and say, that's where I want to go to college. Let me in. I'm in the top third of the high school class. And the system was designed to be tuition free. In 1960, the idea was that higher education is not a privilege, it is a right. That everyone who's capable of going into higher education should be able to do it no matter what their financial circumstances. And so there was no tuition. In fact, today, this may surprise you, there's no tuition at Cal State. There's only fees. Fees were always allowed to make up for things like dormitories, which obviously cost to run, or the food court, or the basketball court, or the athletic center, so the health center. So fees were always allowed, and somehow fees have crept in, and now they pay for much more. In fact, now you pay with your hard-earned money, or with your parents' hard-earned money, 50% of the cost of producing your education. So now the system is so different. You pay half of the cost when you were supposed to pay nothing. Thanks to those 2 gentlemen, actually quite largely, who were really instrumental in this process. Think about that next time you vote for an actor. And what's really sad, and that's why I'm bringing this up, is that you, you're not getting what you're paying for. So if you look at how this course was run, there's 180 students, many of whom, have kind of given up. There were graders who got paid to spend about 1 minute per homework, 1 minute for the draft, 1 minute for the final. That's what they got paid for. That would explain why they have given you such cutting and incisive comments about your coding skill, because they didn't have time to do anything else. That's why it's all automated. There are lab assistants who get paid literally minimum wage, and they were very nice lab assistants, but they didn't really have the time or initiative or incentive or remuneration to do a better job advising you on the labs. And so, the labs were what they were, but they could have been much better. The tutors were unpaid. And what we used to have is we used to have lab assistants who got paid a lot to prepare for the classes. We used to have graders who would actually write meaningful comments about everyone's submissions. We used to have tutors who were paid and who were there to help everyone who needed help. We used to have mentors who were especially there for those students who came from maybe not so great high schools and who needed some extra help. And so there used to be money for all of that. There still is money for all of that if you go to another university. If you go to Stanford, for example, and you look at how CS2 is taught there, it's also one guy in front of actually 1,000 students. And then an army of about 100 undergraduate assistants who helps these students. In Berkeley, the numbers aren't quite as good, but it's like that. Here, it's been cut every semester, and now we are where we're at. And so, I'm very sorry that I couldn't give you a better course, but there's only so much one can do. And it is a scandal, and you have every right to assume that this is not normal. This is not how it should be. This is, in fact, not how it should be. Finally, when you look at the schedule for next semester, you will notice that about 4 out of 5 of the undergraduate classes, that's your classes, are taught by what's called adjunct professors. I don't know if you understand the system with adjuncts. So it used to be that to be a university professor, at least you had to know some amount of stuff and have a PhD, which may not be the same thing. And you're supposed to do some research or actual industrial experience. But nowadays, most of the undergraduate education is given by people whose qualification is willingness to work for $5,000 a course. That's what they get paid. I get paid more than that, fortunately, otherwise I wouldn't be doing, well, I'm still doing it out of charity, but so more likely than not, you're going to have a whole bunch of people who get paid very little money, who may or may not know what they're doing. Some of them are total saints. And so if you have one, thank them profusely. They do it because they love teaching. They love the subject matter, and they love teaching it, and they take the insulting pay that they get. They just deal with it. There are others who stitch a life together by going to 5 or 6 or 7 universities and community colleges and teaching courses at $5,000 a pop. You have to teach a lot of courses at $5,000 a pop to make a living in the Bay Area, and they have no time to do anything other than read you the PowerPoint slides. And so when you register for a course, you need to eyeball and see what it is that you're getting. And it's very sad, and it's not what it's supposed to be. You have every right to demand something better, and I hope some of you will. And so what really matters is you're unfortunately in a system where you have to learn to teach yourself. You're going to have to simply live with the fact that you want to go from here not just to a piece of paper, because what are you going to do with a piece of paper? You can't eat your diploma. Your diploma doesn't generate cash. It only does so when you've actually learned what you need to get employed, where you can put the stuff to use. So you're unfortunately going to have to learn much more than many of you have to teach yourself and to teach each other. This is how it's been in third world universities since the beginning of time, that the students taught each other and the professors were somewhere, and that is where we're moving to. And so you're going to have to really do that. You have to network and collaborate. And that's why I was unhappy with some people making a mess out of Piazza. Piazza is there as a training ground for what you will need to succeed in the next 2 years. You will need to work with each other in a productive way and not, try to chase this silly point or that. You really will need to be able to work with each other and help each other out, because in quite a few of the courses that you're going to be taking, you are the only ones who are there. There's someone reading you PowerPoint. Hopefully a nice person. And so, write lots of code. When you write code, you know whether you did it right. Do something in your classes, do something out of your classes. There's good opportunities where you can work with business students to do some kind of, they'll have like an entrepreneurship program or something where they do hack out some code, and the business person is actually invaluable because they find the money and that kind of stuff. Do those things, do the hackathons, work with each other. Hopefully you'll have a good number of good instructors, and you'll be able to survive the not so good ones. Good luck, you'll need it.